One positive consequence of having lazy evaluation is that we find that we can have infinite lists in Haskell. Let's see what that means. So we can write a definition like ones equals 1 colon ones. I mean, it's a perfectly good recursive definition. If we were to evaluate it fully, it would produce something infinite. In a similar way, nat equals 0 colon map plus 1 along nats. The first element of nats is 0, so the second element is going to be 1, and so on. But if we are to evaluate those things fully, the evaluator goes away forever. But that's not how things work in Haskell. We only evaluate things as much as they are needed. So for example, if g of x colon y colon z is x plus y, it sums the first two elements. What is g applied to ones? It's 2, because we evaluate ones once, and then we evaluate the inner ones, and then we see that ones begins 1 colon 1, and then we can say the result is 2. In a similar way, we can say that the result of g of nats is 0 plus 1. And then we get very nice examples of how to use infinite lists to give us finite results. So one way of summing the first n natural numbers is to generate the whole list of natural numbers, take the first n and sum them. And that will only generate those first n natural numbers and will sum them. So that's another way of defining a list of numbers from 1 up to n. Define the list of all the nats and take the first n. So a rather more sophisticated use of infinite lists is this. It's the infinite list of prime numbers. So primes defines a list of integers. And primes is got by sieving the list of all the numbers from 2 upwards, to 2, 3, 4, 5, 6, and so on. And what does sieve do? Sieve, the idea of a sieve is that it allows some things to go through and some things are blocked. And when we sieve a list, we take the first element of the list and then we remove all the multiples of that from the list. So here's the definition of sieve. Sieve applied to x colon x's, so sieve with a list whose head is x and tail is x's. The head of the result is x, and then we call sieve on, not on x's, but on this list. We choose all the y's in x's so that y mod x is bigger than 0. If you divide x into y, there's a positive remainder. That is, y is not a multiple of x. So the only y's that remain in the list that is subsequently sieved are numbers which are not multiples of x. So first time round, we remove all multiples of 2. And then we call sieve on a number, on a list whose first element is 3. So that removes all multiples of 3. And you can see that similarly, we'll next call sieve with a 5 at the head, and 7, and then 11, 13, 17, 19, 23. 25 will have been removed because it's a multiple of 5. And so any number we hit that is a composite will have been removed by removing all the multiples of one of the factors of that number. So that's how, and this is Eratosthenes is a Greek mathematician who defined an algorithm like this. There are people who say this isn't quite the sieve, but this certainly is a nice way of describing directly the list of prime numbers. It says systematically remove all multiples. When you find a prime, output it and then remove all its multiples. And that's what the sieve function here does. Okay, so those are a number of examples of working with infinite lists. Next, we'll talk about streams, which is a sort of variant of doing things on infinite lists.